The Pantheon in Rome has a dome that's 2,000 years old, and there's no steel inside it, it's concrete, and it's still standing where so many others have collapsed. The concrete itself, it has a special recipe. It actually gets stronger as it ages. And then there's the hole in the roof, that giant opening. It's not a mistake. It's a key part of the engineering, it's what helped it last. So it's a combination, ancient genius, and also historical fortune. That's what made this possible. For a human creation to become timeless, standing right under that dome, it doesn't feel its age. Inside, it's less a building and more its own world, a perfect sphere of space cut from stone and light. The only direct light comes from that single beam above, from the Oculus, a celestial spotlight. It sweeps slowly across the floor and walls, marking the hours. That effect is possible because of the dome's scale, a record it still holds after 2,000 years. Its diameter is exactly equal to its height from the floor. That creates the harmonious spherical interior. To put the size in perspective, you could fit the entire Statue of Liberty inside, torch to toe, comfortably. It remains the largest concrete dome ever built. What's revolutionary isn't just the ambition, it's the puzzle it presents. Every modern engineer knows the rule for large concrete structures. You have to reinforce them. Steel rebar is embedded inside to handle tensile forces. The pulling and stretching stresses concrete is weak against. Without that internal skeleton, a massive concrete dome should crack and collapse under its own weight. The Romans had no rebar. They had no steel beams, yet they built this, and it stands. So you have to ask, what did they understand that we're only recently rediscovering? Their genius wasn't in defying physics. It was in collaborating with it, through form and material. The perfect hemispherical shape is the first clue. That geometry is inherently strong. It channels the immense downward force into compressive stresses, which concrete handles brilliantly, pushing straight down the curving walls into the massive drum below. The builders worked with an intuitive sculptural understanding of load paths, crafting a shape that naturally wanted to stand. So we're left with this architectural anomaly, a monument that shouldn't exist by conventional wisdom. Its survival whispers of secrets locked in the fabric of its construction, starting with the concrete itself, which was far from ordinary. The recipe for that concrete was lost for centuries. At the base of the Pantheon's drum, workers weren't just mixing sand and water. They were blending a precise formula. Lime, volcanic ash, chunks of stone. That's opus Roman concrete. Its key ingredient was pozzolanic ash from the volcanic hills near. Mixed with lime and water, it starts a chemical reaction. A reaction so strong the concrete can cure underwater, forming a solid rock-like mass. But its real magic is longevity. The Portland cement we use today is different. It can be stronger at first, but over decades it gets brittle. It cracks, corrodes from water and salt. Roman concrete does the opposite. Over centuries, as water seeps into its tiny cracks, it reacts with the leftover ash and lime. That forms new interlocking crystals. A mineral called aluminous. These crystals fill the gaps. They heal the concrete from the inside. Scientists call it a self-healing property. The dome isn't just resisting time. It's actively repairing itself, getting subtly stronger with every rain that comes through the Oculus. And the Romans didn't use this material uniformly. They were strategists about weight. Look at the aggregate, the stone, rubble in the mix. At the heavy base of the dome, they used dense basalt. As the walls curved up, they switched to lighter bricks and tiles. And at the very top, near the Oculus, the mix is full of porous, feather-light pumice. This gradation was deliberate, a way to lighten the load on the structure without losing integrity. So the first pillar of the Pantheon's survival isn't a secret of shape, but of substance. A lost material science that built resilience into every cubic foot. But even the best material needs intelligent application. And that leads to the second, even more clever layer of the design. The material science was only part of it. You look up at the ceiling. Those 5 rows of sunken panels, the coffers, they make this honeycomb pattern. People talk about the beauty, the geometry, but the purpose was practical. It's the sign of a weight-saving strategy. The dome isn't uniformly thick. Down at the base, where it meets the drum, the concrete is over 20 feet thick. A huge ring of stone, but it tapers as it goes up, deliberately. By the time you get to the top, to the Oculus, the shell is only about 4 feet thick. That thinning wasn't a shortcut, it was physics. The lower parts carry the weight of everything above. They need to be stout like a tree trunk. Higher up, the load lessens, so you can reduce the material. They were optimizing the form, using material only where it was needed. And then the coffers. Each recessed square is carved out of the concrete. But it wasn't carved after. The wooden framework for the wet concrete was built with these shapes already in it. Every coffer is a bucket of concrete that was never poured, weight that was never added. It's like slicing holes in a thick piece of cheese. You take material from the center where it adds less strength, but you leave the rims intact. The coffers do that. They turn a solid slab into a latticed shell. It dramatically reduces the dead load, the permanent weight of the structure itself. This was empirical engineering. They didn't have stress diagrams, but through observation they understood a lighter dome was a safer dome, one that would push less on its walls. This geometric optimization solved one problem, but it created another. By making this heavy crown, they generated an immense lateral force. A silent, persistent push trying to burst the walls outward. Containing that thrust became the final act. The real danger is that silent, outward push. A dome wants to spread. It wants to flatten out. And if the walls holding it can't resist that horizontal force, they'll bow outward. They'll collapse. The Pantheon's answer is its most overlooked feature. The massive cylindrical drum it sits on. From the outside, it's a solid, unbroken ring, 20 feet thick of brick and concrete. That's not just a wall. It's a continuous restraint. A giant belt cinched tight around the base of the dome, containing its ambition. But the Romans knew a solid block of material that size would be its own problem. The weight would be immense. It could crack under internal stress. So they did something. They built voids into it. Within that seemingly solid drum are hidden chambers, hollow spaces, arched recesses. Some are the side chapels you see inside. Others are structural voids, never meant to be entered. And woven through the walls are relieving arches made of brick. You can sometimes see their outlines in the masonry. They're not decorative. They act like an internal skeleton. When the dome pushes outward, these arches channel that force. They gather the stress and redirect it, guiding it along specific, stronger paths down through the piers of the drum and into the foundations. It's a system of passive reinforcement. The voids and arches lighten the overall load, and the remaining solid sections form a network of super strong vertical supports. Think of a modern bicycle wheel. The rim is under tension from all the spokes, but that tension is what gives it strength, keeps it perfectly round. The Pantheon's drum, with its network of arches, works on a similar principle, distributed force. It transforms a dangerous, diffuse push into manageable lines of compression. This was intuitive structural engineering. They couldn't calculate the forces, but they could design a system to absorb them, to redirect them. This hidden latticework is the final piece of the static puzzle. It's why, for centuries, the dome has rested securely. Its outward thrust silently neutralized by the intelligent design of the drum beneath it. But a building doesn't exist in a perfect, motionless world. It has to endure the tremors of the earth itself. The Pantheon needed solid ground, and it got it, geological luck. It sits on the Tiber River's old floodplain, this deep layer of clay and sand and gravel. It's been stable for 2,000 years. It doesn't shift with the seasons. It doesn't swell with rain in a way that would twist the footings. The Romans picked the site for its sacred importance, not the soil. But the ground underneath cooperated. It was a kind of historical fortune, and then they built on that fortune. They prepared the site. Before the main structure, they dug a huge circular trench wider than the building. They filled it, layer after layer of concrete and crushed stone. This wasn't just a base. It was a giant, rigid raft. Its job was to spread the weight over 20,000 tons across a huge area of that stable soil, to prevent uneven settling, the kind that cracks walls. The foundation mediates. It transfers the load evenly to the earth, so there are no points of high stress. Then there's the earth's own threat. The Mediterranean has earthquakes. Rome has been spared the worst ones. Its location has seen only low to moderate seismic activity over the centuries, and when tremors did come, the Pantheon's design helped. It's monolithic. The dome and the wall are one solid mass of concrete. That was an advantage. It didn't act like separate blocks that could grind and fall. Instead, the whole structure could sway as one unit, like a heavy tree bending from the roots. That flexible raft foundation allowed a little movement. The building could rock slightly on its base, dissipating the energy through its whole body, instead of letting it concentrate and shatter something. So you have this combination: stable, forgiving ground, a foundation made to spread weight and allow movement, and a location that avoided the worst geological violence. That's the silent, external condition for lasting. But a building is more than that. It's a story. and the Pantheon's story took a turn. It became a living monument. That gave it a different kind of protection. The Pantheon's strongest defense might have been its purpose. It never fell into ruin. As the empire faded, the building was given a new life, a new identity, and that guaranteed its survival. In 609, it was consecrated as a Christian church, the Church of Saint Mary and the Martyrs. That act was a kind of historical safeguard. It turned the Pantheon from a relic of a pagan past into a vital part of a living community. Its doors stayed open. Its space was used and cared for and revered. That continuous chain of occupancy is a fourth pillar of its longevity, just as crucial as the concrete or the coffers. You think about other classical structures. Abandoned buildings are quickly undone. A single broken tile on a roof lets in water. That water freezes and thaws, prying stones apart. Weeds take root in cracks, their roots acting like tiny wedges. Without someone to sweep the floors, decay sets in fast. A building left alone is a building beginning to die. The Pantheon was spared that. As a church, it had a congregation. It had a reason to be maintained. Roofs were repaired to keep people dry. The bronze doors were kept in working order. The marble floors were swept. The Oculus, that great opening, required its own care. To make sure rainwater drained and didn't pool inside. This wasn't grand restoration. It was simple, steady stewardship. The kind that comes from a place being loved and used every week. This reuse provided a shield. In times when ancient monuments were plundered for marble or stripped for metal, the Pantheon was protected by its sacred status. It wasn't seen as a quarry of old stone. It was a house of worship. That identity commanded respect. It offered a legal and social protection that ruins didn't have. The act saved its physical fabric. The building's meaning evolved, but its essence endured. This unbroken thread of purpose from ancient Rome to now is a lesson. A structure is most vulnerable when it's forgotten. The Pantheon was never forgotten. It was always someone's responsibility. That constant attention over centuries prevented small problems from becoming catastrophes. It meant that when the great tests came, the building was still whole, still strong, ready to face them. Rain isn't something this building fights, it's treated like a guest. That Oculus, that huge open eye in the roof, it welcomes the rain in. When a storm comes over Rome, water pours through that opening, 27 feet across, just pours down. It looks like a mistake, a roof with a giant hole. But the Romans didn't think of water as a threat. They saw it as a force you could guide. So they designed the whole interior around handling it. That's the fifth defensive factor, a built-in, living system for dealing with the elements. The Oculus does more than let in light and rain. It works as a natural pressure valve. The dome is sealed except for that one opening. So when the wind blows outside or when the air pressure changes with the weather, that opening lets the pressure inside equalize. The air inside doesn't get trapped and push against the dome. That subtle pressure difference, the kind that can stress a sealed structure, it just vents out. The Oculus lets the building breathe. It prevents a different kind of strain, atmospheric compression. But the water still comes down, and that's where the floor takes over. If you look down, the marble panels aren't laid flat. They're set on a very slight slope, a gentle, almost invisible gradient that runs from the walls toward the center of the room, and at certain points there are 22 small holes. They're not damage, they're drains. When rain hits the floor, it immediately starts to move. It doesn't pool, it doesn't sit. It flows along the channels between the marble slabs, finds those holes, and disappears into a hidden system below. That's proactive defense. The biggest threat to ancient masonry isn't time, it's water. Water that seeps into cracks, freezes, expands, and pries the stone apart. That cycle of freezing and thawing. By designing a floor that gets rid of water instantly, the builders removed that threat at the source. They anticipated the climate. They worked with the reality of rain instead of trying to stop it. That idea of cooperation applied to the materials inside, too. The walls are lined with marble and granite. They weren't just chosen for beauty. They were chosen for endurance. They're impervious to damp. They can be washed, century after century, without wearing away. The whole interior is a machine for weathering storms. A system that recognizes nature's power and gives it a clear, graceful path to follow. The building doesn't fight the elements. It receives them, it honors them, and it lets them pass through. Because of that, it stays dry, it stays stable, it stays whole. That harmony between design and environment, it's a quiet masterpiece of foresight. It turned what looked like a vulnerability into a source of strength. The marble feels cool even on a hot day. That's the marble cladding. Every wall, from the floor up to the dome, is covered in polished slabs. Red porphyry, green serpentine, a creamy yellow stone. For centuries, people saw that as pure decoration, just opulence. But it served a hidden function. It was armor, interior armor. Beneath it is the vulnerable core, the porous concrete, and concrete breathes. It absorbs moisture from the air. In Rome's climate, with the humidity and the temperature swings, that absorption would be constant. The concrete would slowly drink in dampness, then dry out, expand with heat, contract with cold. Over centuries, that cycle causes fatigue. Tiny cracks form, they widen, they weaken the matrix. The marble cladding stopped that cycle at the surface. It created a seamless barrier, an impermeable skin that sealed the concrete away from the interior environment. The humidity in the air, the breath of visitors, the subtle temperature changes, they met the marble first. The dense stone acted as a buffer. It stabilized the microclimate right at the wall's surface. That drastically reduced the stress on the structural core, the thermal stress, the moisture stress. So the concrete behind the marble exists in a state of equilibrium, shielded from the daily wear of the atmosphere, and the marble itself was chosen for endurance. These weren't local stones, they were imported from Egypt, from Greece, from North Africa, selected for their density, their hardness, their resistance to wear. They were a permanent finish. Softer stone might have powdered or stained over centuries of handling, but these surfaces remained intact. They could be cleaned and polished without degrading, which meant the protective barrier never failed. For 2,000 years, that interior armor has done its silent work, preserving the strength of the walls behind it. It's a lesson in design where even the beautiful surfaces were engineered for preservation. But there was another threat the builders had to consider, a more insidious one. The threat of metal and its slow, inevitable betrayal. That marble inside wasn't just a shield for the concrete. It protected it from something the Romans never actually faced: corrosion. And that leads to a pretty startling fact. The Pantheon doesn't have a hidden skeleton. There's no internal steel framework. And in a profound way, that's one of the biggest reasons it's still here. We build differently now. Our concrete is almost always reinforced. We put steel bars, rebar, into the wet concrete. The steel takes the tensile forces, the pulling. The concrete handles the compression, the squeezing. It's a powerful partnership. It lets us build taller, thinner shapes. But it comes with a hidden timer, a built-in flaw, and that timer is rust. Concrete isn't perfectly waterproof. Over decades, moisture finds a way in. It seeps through tiny cracks, through pores. And when that moisture reaches the steel rebar, a reaction starts. The iron oxidizes. It rusts and rust expands. It can grow to several times the steel's original volume. That expansion creates huge pressure from inside the concrete. It pushes outward. It cracks the concrete from the inside. This process is called spalling. It's the main cause of failure in modern reinforced concrete. It's a slow internal decay. The very thing that gives the structure its strength becomes what makes it fall apart. The Pantheon avoided all of that. Its builders took a different path. They accepted a limitation, concrete's weakness in tension, and they designed around it. They made a shape, that perfect dome that turned all the major forces into compression. Forces concrete can handle forever. Their strength came from geometry and mass, not from a hidden metal frame. So there's no internal metal to rust, no corrosion clock buried in the walls. When water comes through the Oculus, it runs over marble and drains. If some moisture ever reaches the concrete core, there's nothing there to corrode. No expansion, no internal cracking. The concrete gets wet and then it dries, that's it. This is a huge case of less being more. By skipping the reinforcement we use today, the Romans avoided its worst failure. Their idea was one of monolithic permanence. Build something so massive, so intelligently compact in its form that it just becomes a permanent part of the landscape. A mountain, not a machine. That's the leap we're only now really seeing. We engineer for a design life. 50 years, 100. The Romans with this seemed to engineer for forever. They built in a conversation with time, using materials and forms that age not into weakness but into a kind of stony strength. The lack of metal isn't a missing piece. It's the mark of a different kind of genius. One that makes you rethink what strength actually means across centuries. They built without equations, no stress formulas, no computer models. The Pantheon stands as a testament to a different intelligence, a practical wisdom passed from master to apprentice. This is the sixth pillar of its survival: empirical engineering, a culture of learning by doing, refined over generations. Picture the architects. They didn't have our mathematics. They couldn't calculate the forces in a curved shell. They worked from observation, from memory, from a shared library of what had worked before. Their tools were proportional rules, simple ratios, a mental catalog of precedent. They knew for a dome of a certain span, the walls needed a certain thickness. This wasn't a theoretical law. It was a rule of thumb born from seeing what collapsed and what stood. These relationships were the guarded knowledge of the building guilds, trade secrets, refined through trial and error on countless projects, baths, basilicas, aqueducts. Each successful structure added to a collective understanding of scale and stability. The Pantheon's proportions aren't random aesthetic choices. They're the result of that accumulated wisdom. The dome's height equals its diameter. The drum wall's thickness relates to the dome's span. The oculus is a specific fraction of the whole. These weren't just pleasing to the eye. They were structural prescriptions, ratios that experience had shown would produce a stable form. This empirical approach let them design a shape that naturally channeled the immense forces along the right paths. They created a geometry that wanted to stand. It was a pre-scientific understanding of compression flow. They couldn't name the physics, but they could sculpt a form that obeyed it. Their success becomes more remarkable when you consider other ambitious domes. History is littered with them, structures that pushed the known rules and failed. The original dome of Constantinople collapsed not long after completion from an earthquake. It was later rebuilt with a different design. Closer to Rome, the Basilica used similar vaulting technology, but on a less perfected scale. What separates the Pantheon is the refinement of its empirical recipe. It represents the peak of a long tradition, where every previous mistake and success was baked into its design. This invites a reflection. We live in an age of precise calculation. We model structures down to the millimeter, yet our buildings are often designed for a century, not a millennium. The Roman approach was different. It was about designing for permanence by adhering to time-tested principles. Their confidence came not from a spreadsheet, but from a lineage of hands-on knowledge. The Pantheon is the ultimate argument for that kind of wisdom. It's the masterpiece that survived where others fell, because its builders listened to the silent lessons of every stone that had come before. Their genius was in trusting what worked and refining it to its most elegant, enduring form. Not every Roman dome lasted. You can go to the baths of Caracalla. The walls are still there, the arches. But the ceilings, the big vaults over the main halls, they're gone. Just open sky now. Same thing at the Temple of Venus in Rome near the Forum. It had this grand double design, but its concrete roof didn't make it. These are skeletons. They tell a story of collapse, not survival. And looking at these fallen buildings shows you what the Pantheon did differently. It wasn't one secret. It was a chain of choices. Break one link and the whole thing could have failed. Take the materials. In a lot of other buildings, the concrete mix was more generic. Builders might have used whatever local stone was cheap. They might not have graded the lightweight aggregate carefully. Or they skimped on the pozzolana ash. That's the key ingredient. It gives the concrete its self-healing strength. A weaker mix makes a more brittle shell. It can't handle the slow shifts in the ground or the steady creep of its own weight over hundreds of years. Location was critical. The Pantheon sits on that stable old floodplain. But other big projects were built on filled land or on hillsides with unstable ground. If the foundation settles unevenly, even a few inches difference in one corner, that's a silent killer. It introduces twisting forces, torsion. Even a well-designed arch can't withstand that. Cracks form, they widen, and the structure gives way. Then there's the support system. The Pantheon's drum is a masterpiece of hidden buttressing. But other large vaults, like in the baths of Diocletian, they relied on external walls, or they were part of a complex of buildings. When those surrounding structures fell apart or were torn down, the vaults lost their support. They were exposed. Their lateral thrust had nothing to contain it. Sooner or later, they'd push the walls outward and collapse inward. Maybe the biggest difference was what happened after construction. The Pantheon was consecrated. It was cared for, used continuously. A lot of other great domed buildings were abandoned. When a roof isn't maintained, decay accelerates. Water gets in, frost works on it. Weeds and trees take root. And maybe most destructive, these places became quarries. For centuries, builders would scavenge the marble facings, the iron clamps, even the stone blocks themselves for new projects. Stripping the structure like that left the core exposed and weak. It hastened the collapse. The Pantheon's sacred status protected it. Its materials weren't for the taking. All this points to one last subtle factor: the way it was built. Historians and engineers now think it was built in stages. There were long pauses between each massive ring of concrete. This method, incremental loading, let each layer fully cure and settle before the next huge weight was added. The concrete could reach its full strength. The foundation could gradually consolidate under the load without the shock of bearing the whole dome's weight at once. Other projects built on deadlines with less patience might not have allowed for that slow process. The internal stresses from rushing could have created weaknesses from the very start. So the Pantheon's longevity isn't a foregone conclusion. It's the product of a rare alignment, the right recipe in the right place with the right shape and the right support, then the right historical fortune and built with the right patience. It's the one that survived the filter of time because every link in the chain held. That makes its presence today not just impressive but almost miraculous, a single surviving witness to a world of vaulted ambition, most of which is just pieces on the ground now. That patient approach might be the last piece. The seventh insight is about time, not just how long it's lasted but the time it was given to be born. We see building as a straight line. You start at the bottom and go up without stopping. But the Pantheon's builders might have understood something about their material. They might have built in stages with intentional pauses. The method of incremental loading and curing. Think about the wooden centering, the temporary frame that held the dome's shape. It wouldn't have been one huge shell built all at once. That would have been enormous. Instead, the theory now is they built it ring by ring. They'd pour a horizontal layer of concrete, maybe 5 or 6 feet high, into the forms. Then they'd stop. They'd wait for that ring to partially harden, for the chemical reaction in the concrete to progress, for it to get strong enough to hold itself up. Only then would they build the wooden forms for the next ring above it. They repeated this, moving upward in circles like coiling a clay pot. This slow, staged method had a key benefit. It prevented shock loading. If you pour a massive, wet concrete dome all at once, the bottom layers are instantly crushed by the weight of everything above. That wet concrete, before it cures, is weak. It can deform under that sudden load. It can develop internal stresses, micro-fractures that become weak points later. By building in rings with pauses, each new layer was placed on a base that had already gained strength. The lower ring had already started to bear its own weight. It was ready to take more. The load was added bit by bit, gently. The structure trained itself to carry its final weight. It grew into its strength. And this process was tied to the concrete itself. Roman concrete doesn't cure in days. It cures for years, decades. The long-term chemical reactions that give it self-healing properties are slow. So during construction, and long after, the dome wasn't a static, finished object. It was a living material, gradually hardening, settling into its final form. This philosophy of slowness served eternity. It's a sharp contrast to modern construction where speed is usually the main goal. We pour concrete that sets fast, we strip the forms quickly, we load the structure almost right away. The Pantheon shows that some materials, some ambitions, need a different relationship with time. The builders weren't just putting up a building. They were cultivating a monument. They gave it the time it needed to become what it was meant to be. That patience built into the process might be the quietest, most powerful reason it's still here. It was never rushed. It was allowed to become strong. The circle at the top, that opening, is the last piece. It's 27 feet across, and it's more than just a window. It's the keystone for the whole dome. In a normal stone arch, the keystone is that wedge at the very top. It's the final piece. Its weight pushes down on the stones on either side, locking everything into compression, so nothing can move. The Oculus does that same job, but in a kind of inverted way. It's a keystone made of nothing, an absence. The opening is surrounded by a thick, solid ring of brick, and this heavy ring is under huge compression from the weight of the dome all around it. That compression squeezes the ring inward, making it incredibly tight. It cinches the top of the dome shut, like a tight band around the top of a balloon. That compressive ring stabilizes the very top. It completes the hemisphere by giving it a rigid, unyielding boundary. Without it, the top of the dome would be the weakest point. That's where cracks could start and radiate outward. The Oculus ring stops that. It locks the geometry, but the genius is doubled. By removing the concrete that would have filled that center circle, the builders did something remarkable. They took away the most problematic weight. The very center of a dome is where the forces are most complex, where stability is hardest to achieve. By cutting it out, they eliminated that whole challenge. They turned a potential weakness into a source of strength. And light, it's doing more with less, taken to an extreme. The most stable part of the structure is the part they didn't build. And that philosophy of intelligent removal didn't stop at the big scale of the Oculus. It went all the way down to the microscopic, to the very recipe of the concrete, and the careful choice of what they put into it. Layer by deliberate layer, the dome's strength is in its layers, like the rings of a tree. To understand it, you go from the bottom, from the drum, all the way up. If you took a coarse sample straight through the concrete, it wouldn't be uniform. You'd see a gradation. A deliberate shift from heavy to light. At the very bottom, where the curve meets the wall, the concrete is dense, a formidable mass. The aggregate there, the stone mixed in, is travertine and basalt. Some of the heaviest stones, they act like anchors. That dense base is the foundation. A broad, stable platform meant to bear the load. It's the bedrock of the system. Then as you move upward, following the curve, the mix changes. The dark basalt gives way to lighter stone. Tufa appears, a volcanic rock full of air pockets, and fragments of brick and tile, recycled material. These are lighter than the travertine below, but still strong. This middle zone is a transition, balancing weight and integrity. Now higher, near the top, just beneath the Oculus. Here the mix transforms. The aggregate becomes almost feather-light. It's dominated by pumice, that frothy stone that floats on water, and porous ceramics. The material they could use and still call it stone. The concrete here is more air than rock, a deliberate lightness. This vertical layering wasn't an accident. It was calculated. By grading the materials from heaviest at the bottom to at the top, the builders did something. They lowered the dome's center of gravity, like a weighted doll that rights itself. A lower center of gravity creates stability, makes the structure less top-heavy, less likely to push outward. But it goes further. This gradation created a self-buttressing form. The heavy base wants to stay put, seated on the drum. The lighter layers above exert less force, less downward and outward pressure. That systematic reduction in weight minimized the lateral thrust, the outward push, that the walls had to contain. They designed the problem out of the structure before it became one. It's a holistic design, in stone and mortar. Every component, from the densest travertine to the pumice, had a role. They weren't just building a shape. They were composing a kind of symphony, of mass and void, density and lightness, where the material itself became an active part of the stability. It shows a mind that saw the dome not as one object, but as a vertical landscape. Each layer adapted to the stress it would hold. Forever, that final lightness at the summit, it's a physical idea. Philosophy made of stone, but philosophies need believers, and in the Renaissance, the Pantheon found them. It became more than a building, it became a teacher. An entire generation of architects looked at it and saw a blueprint, a new world. This reverence became its eighth shield. For someone like the Pantheon was a riddle. He traveled to Rome. He studied its curves, measured its proportions. He was trying to understand how it stood, because he wanted to build the dome for the Florence Cathedral. He didn't copy it, he couldn't. The technology was lost, but he learned from its logic, from its confidence. The Pantheon proved that such a span was possible. It was a silent mentor, giving permission to dream on a colossal scale. Michelangelo would later call its design angelic, not human. And that wasn't just poetic praise, it was a declaration, a sacred status in the new artistic religion of the Renaissance. To these masters, the Pantheon was the ultimate classical text. A manuscript written in geometry and light. Their pilgrimage to Rome was a journey to read it, and this cultural veneration had a direct consequence: preservation. The building was no longer just a useful church, it was a monument to human genius, a relic of a golden age they were trying to revive, so when it needed care, the approach changed. It became conservative, respectful. The popes of the era ordered repairs, but these were acts of conservation, not reconstruction. The great bronze doors were maintained. The marble inside was cleaned and secured. The portico's columns, each a single piece of granite, were checked for stability. The interventions aimed at one thing: keeping the original form intact, letting the ancient voice speak clearly. There were, of course, additions. In the early 1600s, Pope Urban VIII commissioned twin bell towers for the facade, designed by. They were meant to update its profile, but later generations saw them as incongruous. They were removed in the late 19th century. a testament to the enduring power of the original design. Even the Baroque era's flair ultimately bowed to the Pantheon's older authority. This period something crucial. It established the Pantheon as an untouchable masterpiece. Its value was now twofold, a functioning church and an irreplaceable piece of human heritage. This dual status guaranteed it would remain a priority. It ensured that funds and expertise would always be directed its way. The building was wrapped in a new kind of protection, the protection of immense cultural importance. It had survived the fall of an empire and the neglect of the Dark Ages. Now it was celebrated, studied, cherished. Its future was secured not by mortar but by memory, and this legacy of scrutiny set the stage for its next chapter. When the age of science arrived, it turned its analytical gaze not to destroy the mystery, but to finally understand it. Laser light traces the curves now, where ancient hands once shaped wood. In the 21st century, the Pantheon gets its most careful look yet. Engineers and archaeologists arrive, but not with chisels. They bring technology that sees without touching. Terrestrial laser scanners spin slowly in the center of the rotunda. They fire millions of points every second. They capture every imperfection, every subtle deviation. They map the dome's surface with sub-millimeter precision. And that data builds a digital twin, a perfect virtual replica. That's where the real interrogation starts. Using finite element analysis, a computer modeling technique, scientists can apply virtual forces to this model. They can simulate earthquakes. They can test wind loads. They can map the flow of stress through every inch of the structure. It's like we can finally ask the building questions and watch it answer. The answers come in shimmering, color-coded diagrams of force. What the models show is astonishing confirmation. The stress distribution inside the dome's shell is almost perfectly uniform compression. There are no hidden points of high tension, no dangerous pockets of shear waiting to fail. The Romans, through empirical genius, crafted a shape that naturally channels all the major forces into a smooth, downward flow. The computer quantifies what the eye intuited. The gradation of materials, from heavy basalt at the base to light pumice at the top, shows up in the models. It shows a masterful balancing act. It minimizes internal bending moments, those twisting forces that can crack concrete. Non-destructive testing adds another layer. Ground-penetrating radar peers into the thick drum walls. It confirms the presence of those hidden voids and brick arches. Thermal imaging cameras map how the building breathes over a day. They're sensitive to minute temperature differences. They show how heat from the sun moves across the surface. They show how the massive thermal mass of the concrete buffers these changes. It prevents the kind of rapid expansion and contraction that causes fatigue. Even the microcrack patterns tell a story, studied with high-resolution photography. They aren't random signs of decay. They follow predictable paths like seams in a dried riverbed, and they are often filled with the self-healing mineral crystals. The ones Roman concrete is famous for. Modern science hasn't debunked the Pantheon's mystery. It has deepened it. By quantifying the brilliance, it transforms anecdotal awe into empirical respect. We now have the mathematics to describe the intuition. This ongoing dialogue between a 2,000-year-old artifact and cutting-edge analysis does more than solve historical puzzles. It offers a gift to the future. The principles being validated here are informing sustainable architecture today. The efficiency of form, the longevity of material, the wisdom of designing with natural forces, not against them. The search for durable, low-carbon building materials has led scientists back to the Roman recipe. They're actively trying to replicate its self-healing properties. The Pantheon is no longer just a relic. It's a living laboratory, a bridge of stone and data, connecting a profound past to the architectural questions of our future. The data points toward a modern question. How do you build for centuries, not just decades? The Pantheon offers a ninth principle. It stands as a kind of manifesto for sustainable building. In a time of climate urgency, its lessons aren't just historical, they're blueprints. The first lesson is the material. Roman concrete did something we struggle with. It was a low-carbon material made from local things. The pozzolana ash came from volcanoes nearby. The aggregate was often recycled brick or local stone. Producing the lime did release carbon, but the final product locked that away for. Then you look at modern Portland cement, a major source of global emissions. Its production is energy-intensive, and the structures it makes often need replacement or major repair within a human lifetime. The Roman method was circular by necessity, local sourcing, durable results. The second lesson is performance. The Pantheon's passive systems required no energy to run. The Oculus gives daylight and ventilation. The massive thermal mass of the concrete walls buffers the interior from Rome's heat. It stays cool in summer. It holds warmth in winter. This is passive climate control at a master level. It uses the physics of the building itself to create comfort. No fossil fuels, no complex machinery, just design working with the environment. Today, researchers in labs are pouring samples trying to crack the ancient code. They're not just studying history, they're engineering the future. By analyzing the nanostructure of Roman concrete, they want to replicate its self-healing properties. Imagine a future, one that can seal its own microcracks when seawater gets in, extending its life from 50 years to 500. That potential is locked in the Pantheon's walls. This research reframes sustainability itself. We often focus on efficiency, on reducing a building's operational energy, but the Pantheon teaches that durability is the ultimate form of green building. A structure that lasts 2,000 years has an almost immeasurably low impact. It isn't torn down and hauled to a landfill every few generations. It doesn't demand a constant stream of new materials for repairs. Its carbon footprint spread over that immense approaches zero. That's a paradigm shift. From disposable construction to monumental endurance, our modern world is built on planned obsolescence. The Pantheon represents the opposite, a philosophy of care and permanence. It asks us to build heirlooms, not products. That might be its most vital legacy now, a call to build not just for ourselves, but for a chain of generations we'll never meet, to think in scales of time that humble our own brief lives. And yet, that legacy now faces a new kind of threat. Not from earthquakes or neglect, but from the very atmosphere it has weathered for so long. The Pantheon's air isn't clear anymore. It's not the sky of ancient Rome. There's a new threat, invisible. Exhaust from millions of cars, industrial emissions, it all settles on the marble. It's not just dust. It's a chemical film. Sulfur dioxide, nitrogen oxides, they mix with rain and form weak acids. These acids attack the calcium carbonate in the stone. It etches the surface, turns polished stone dull, powdery. Over decades, acid rain can dissolve carving details. It weakens the stone's crystalline structure. The skin that protected the building is now under a silent siege. Preservation teams monitor the stone's surface pH. They watch for changes that signal decay accelerating. The fight is against an enemy the Romans never knew. Beneath your feet, there's another force. The rumble of buses, the thrum of scooters, the steady flow of traffic. It creates a low-frequency vibration through the ground. To us, it's a background hum, imperceptible. But to a 2,000-year-old structure, it's a form of persistent stress, vibration fatigue. Think of bending a paperclip back and forth. It doesn't break on the first bend, but after many cycles, the metal fatigues, it snaps. The micro-vibrations from traffic are like that on a geologic timescale. Over many years, they can loosen mortar joints, propagate tiny cracks, contribute to a gradual weakening of the material. It's not an imminent collapse. It's slow, cumulative wear. Traffic calming measures, restricted vehicle zones around the monument, they're part of the defense now. An attempt to quiet the ground it stands on. Then there's the weight of admiration. Millions of visitors each year. Each person brings a microclimate, body heat, exhaled moisture. Collectively, it raises the interior humidity. That can encourage mold growth on organic residues, stress the ancient materials, the physical touch of countless hands on the marble walls, the slow, grinding wear of footsteps on the original floor. These are acts of love that also cause erosion and crowd dynamics. The density of people during peak hours creates a live load, a shifting weight on the floor and through the structure on the foundations. The building was designed for massive static weight, but the dynamic moving pressure of a dense crowd is a different force. Modern preservation requires managing this flow. Timed entry systems, designated pathways, monitoring visitor numbers. They're the new centering, the temporary framework of crowd control protecting the permanent structure. It's a paradox. The Pantheon survives because it was never abandoned, because people have always come. Yet now, the volume of that devotion is itself a risk. The balance is delicate, keeping it accessible as a living church, a public monument, while preserving it as a fragile artifact. The solution is a marriage of ancient resilience and modern technology. Sensors in the walls monitor crack width and humidity in real time. Air filtration systems in preservation areas combat pollution. The management is a continuous, silent vigil. It acknowledges the greatest threats are no longer cataclysmic events. They're the steady pressures of the age we live in. But the Pantheon has a deep resilience. Its massive monolithic construction, its robust foundations, give it a tremendous capacity to absorb these modern stresses. The original builders provided a buffer of strength so vast. It's only now after two that we must begin to actively manage the slow drip of contemporary life. Their foresight bought us time. Now the responsibility is ours to use it. This is the final insight. The Pantheon didn't survive because of one secret. It survived because of a conversation, a perfect ongoing dialogue between every part of it. That's synergistic integration. The 10th principle: you can't remove one piece without unraveling the whole. The strong concrete made the thin-shelled geometry possible. That elegant shape generated an outward thrust, and the massive hollowed drum was there to contain it. The stable ground accepted that weight. The Oculus relieved pressure and managed water, and the sloped floor whisked it away. The marble cladding shielded the concrete from the interior climate. Its continuous sacred use meant all these systems were maintained, and the staged construction let each layer gain strength before bearing the next. Each factor is both cause and effect. They lock together. The concrete's longevity justified the ambitious form. The form's perfection justified the concrete's cost. The building's beauty and sanctity justified its endless care, and that care preserved the systems that created the beauty. It's a closed loop, a self-reinforcing cycle of stability. This is why modern analysis ends in admiration. Engineers can model one factor like the concrete's strength or another like the dome's shape. But the true magic is in the interplay. The whole is greater than the sum of its parts. You see this synergy in other ancient marvels. In the Great Pyramid's alignment, its massive stone blocks and the dry air that preserves them. In the interlocking stonework of Inca walls, where precision fitting creates seismic flexibility. These aren't collections of good ideas. They're unified systems, philosophies of permanence made physical. The Pantheon is perhaps the most eloquent example of this ancient wisdom. It teaches that endurance isn't a single ingredient you add. It's a relationship you cultivate, between material and form, between structure and site, between a creation and its keepers across time. It's a monument to holistic thinking, to designing not just a building but an entire. This integrated vision is what defies time. It creates something so coherent, so perfectly resolved that decay can't find a foothold. Every potential weakness is guarded by another strength. The system defends itself. And in that silent stone dialogue, you hear the answer to the 2,000-year question. Not how it stands, but why it remains. A testament to what happens when every choice, from the grandest curve to the smallest grain of sand, is made in concert. The in Istanbul. It's another dome that's lasted centuries. The architects there had the same problem, covering a huge space, but they came up with a different answer. They used pendentives, those curved triangles that turn a square base into a circle for the dome. A real stroke of geometric genius. But that first dome from the 6th century, it didn't hold like the Pantheon. An earthquake brought it down. They rebuilt it higher, stronger, with buttresses added later on the outside. So its story is one of adaptation. Later generations shoring it up, changing the original plan. Then there's Florence's dome, a Renaissance answer. The recipe for Roman concrete was lost by then, so he had to invent something new. He built a double shell of brick laid in a herringbone pattern, with a hidden chain of stone and iron inside to hold the tension. It's a dome of intelligence, a lattice of calculated forces, not a solid mass but a cage of masonry. And further east, the great stupas, like at Sanchi or Borobudur. Those are often solid mounds, earth and brick covered in stone, monuments of accumulated mass, reverence made tangible layer by layer. Their endurance comes from that sheer solidity and from being sacred, untouchable. Put the Pantheon next to these. Its path is different. It didn't use pendentives. It wasn't a double-shelled cage. It wasn't a solid, filled mound. Its achievement was this one thing, a perfect hemisphere of concrete, cast as one continuous shell. Where others innovated with form or reinforcement, the Romans went for material mastery, monolithic unity. They bet everything on the integrity of a single substance and the perfection of a pure shape. This isn't about picking a winner, it's about seeing a choice. Each dome reflects its culture's resources, its technological moment, its spiritual ambition. The wanted to dissolve walls with light, a floating canopy for heaven, wanted to prove human genius could match the ancients. The stupas represent the solid, enduring earth of Buddhist teaching. The Pantheon, though, it embodies a Roman ideal, unified, eternal order. The Oculus is the eye of the cosmos. The spherical interior is a model of the world. The material and the message were the same thing. The concrete had to last because the cosmos it represented was eternal, so the engineering wasn't just a technical solution. It was a theological statement, made solid. That cultural vision shaped the technology. They didn't need a complex system of supports because their ideal was wholeness, not complexity. A single, unbroken vault for a single, unbroken realm. Looking at these different paths to longevity, it deepens the wonder. It shows the Pantheon's survival isn't just an accident of good concrete. It was the result of a specific, coherent vision, one that aligned a revolutionary material with a timeless geometric form, all for an idea meant to outlast empires. Its uniqueness is in that complete fusion, where the method of construction became the very expression of its purpose. The cultural vision was the key. The Pantheon wasn't just a building. It was a model of the cosmos, a perfect sphere carved from the world of matter to represent the harmony of the heavens. And that symbolic purpose wasn't separate from the engineering. It was the reason for it. The dome was the vault of the sky. The oculus was the sun, the single source of divine light. The marble floor was the ordered earth below. Every element had a dual role, sacred and structural. This drive to create a cosmic temple didn't just inspire beauty, it demanded perfection. A symbol of the eternal heavens couldn't be flawed. It couldn't risk collapse. That spiritual imperative likely guided every practical decision. The architects weren't just solving a load-bearing problem. They were manifesting a philosophical ideal. The pursuit of geometric perfection, that flawless hemisphere, was a theological act, and that pursuit led to a shape of incredible inherent strength. The proportions weren't arbitrary. The height equaling the diameter creates that perfect internal sphere. This was sacred geometry, a representation of cosmic harmony. But that same perfect sphere happens to be an exceptionally stable form for distributing compressive forces. The symbolic goal and the structural necessity converged. One didn't cause the other. They were two expressions of the same unifying principle. This unity extended to the materials. A temple connecting earth and cosmos required the most enduring substances available. It justified the immense cost of importing rare marbles from across the empire. It demanded the most skilled artisans, the most proven concrete recipes, the most careful supervision. There would be no shortcuts on a project of this spiritual magnitude. The best was the only option. This ensured the physical fabric of the building matched the ambition of its form. The symbolic purpose acted as a quality control mechanism, enforced by faith and imperial will. Even the building's orientation and the light play were part of this cosmic dialogue. On the equinox, the beam from the oculus strikes a specific point above the entrance. On the emperor's birthday, it would have illuminated the doorway. The structure was a giant sundial and celestial calendar, aligning the earthly realm with the cycles of the cosmos. This intertwining of meaning and material created something unique, a monument where every stone served two masters, the gods and gravity. The spiritual significance demanded permanence, and the engineering genius delivered it. This inseparable unity is perhaps why the Pantheon has commanded such reverence through every subsequent era. People didn't just see a clever building, they felt its harmony. They experienced its awe. It spoke to something beyond mere function. That transcendent quality invited preservation. It made people want to care for it, to protect its integrity. The Pantheon survives because it is more than the sum of its parts. It is a perfect idea made solid, a thought about the universe given a shape that the universe itself seems willing to uphold. Even with all our scanning, all our models, the Pantheon keeps its secrets. You can walk into a conference hall, a quiet one where scholars are gathered, and you hear this low hum of debate. It's not about what we know, it's about what we still don't. The monument is here, it survived, that's a fact. But its full story is still just open questions. Each one is a doorway into something deeper. Take the construction. We talk about it being built ring by ring with pauses in between. But the exact sequence, the timing, was it months between layers or was it years? And the wooden centering, that temporary support, it must have been a whole forest of scaffolding. How was it arranged? How did it hold the wet concrete without leaving marks, without causing deformations we can't even see today? Every theory about that process changes how we see Roman project management. Their intuitive feel for material. Then the architect. The inscription says built it, but we know Hadrian rebuilt it entirely. So who was the genius behind Hadrian's version? Was it of Damascus, the famous engineer? Or was it someone else, someone whose name is just lost? And how much did the design change from its original plan? Was this perfect hemisphere always the goal? Or was it an on-site innovation, something they figured out as they went? These aren't footnotes. They point to a moment of creative courage. A decision to pursue an untested form at a breathtaking scale. On a microscopic level, the concrete still surprises us. We've found the self-healing minerals, but the full nanoscale profile, that's still being mapped. Variations in the mix from one batch to another or from one part of the dome to another, they might hold clues. Clues to material science even more sophisticated than we've given them credit for. Were they even aware of these properties, or was it just a happy accident of their recipe? Every new core sample, analyzed with newer tools, adds another piece. It's an ancient material puzzle. Beyond the physical, there are more speculative theories. Some researchers listen not just with lasers but with their ears. They study the acoustics. The dome creates this remarkable sound environment. A whisper at one end can sometimes be heard at the other. Was that intentional? Did the design consider the propagation of sound, chants, oration, shaping it as carefully as it shaped light? And what about celestial alignments beyond the obvious ones? Could the building encode other astronomical relationships, ones we just haven't recognized yet? These ongoing debates, they're not a sign of failure. They're the sign of a living subject. The Pantheon isn't a solved equation in a history book. It's an active conversation across centuries. Every unanswered question is an invitation, a reminder that this building still has things to teach us, about Roman minds, about the nature of materials, about the idea of permanence itself. Fact that it still generates conferences, papers, theories, 2,000 years later, that might be the final quiet proof of its genius. It was built not just to endure physically but to sustain our curiosity. Forever you look at a piece of Pantheon concrete under an electron microscope. It's thousands of times, and what you see is this interlocking crystal structure. It doesn't look like a brittle slab, it looks like a mineral tapestry, and inside that matrix there's a rare mineral. Luminous, its crystals are needle-like. They weave through the material, they fill gaps, they reinforce the whole. And this mineral isn't just sitting there, it's the product of a slow chemical reaction. When water gets into microscopic cracks, it reacts with the leftover volcanic ash and lime. New crystals form, they seal the fissure from the inside out. It's a self-healing mechanism, and it's been active for centuries. So the Pantheon isn't just aging, it's subtly repairing itself. That discovery has turned the building into a living laboratory. Material scientists aren't just studying history. They're trying to reverse engineer a 2,000-year success story. The goal is a new generation of concrete, one that shares this ancient resilience. But the challenge is replicating the process without waiting a millennium to see if it works. Modern Portland cement cures fast. It's strong, but it's also brittle. Its chemistry is largely spent after it hardens. Roman concrete was different. Its reaction was slow. It left latent potential in the material, potential that water could later activate for repair. So now labs are experimenting with modern, industrial byproducts, fly ash, slag from steel production. They're tweaking mixtures, trying to design a concrete with that same capacity for long-term mineral growth. And some of the most innovative research goes a step further, into biomimicry. They look at how the Romans achieved self-healing and ask if we can do it better or faster. One approach embeds tiny capsules of healing agents into the wet concrete mix. These capsules break open when a crack forms. They release a glue-like substance that seals the breach. Another method uses bacteria. Specially selected spores are mixed into the concrete. They lie dormant. When water infiltrates a crack, it wakes the bacteria. They consume nutrients also embedded in the mix, and they produce limestone as a waste product. That limestone fills the crack. It mimics the Roman process, but with biological help. The implications are practical. Imagine protecting a coastal city. Today, and waves attack conventional concrete. Cracks form, steel rebar corrodes. Within decades, you need major repairs or replacement. Now imagine that is made of a modern, self-healing concrete. A storm causes hairline fractures, seawater enters, but instead of accelerating decay, that seawater triggers a healing reaction. New minerals form, they close the cracks, the wall maintains its integrity. It could extend from 50 years to 500. The same principle applies to bridges, to tunnels, to nuclear containment structures, infrastructure we literally bet our lives on. So the Pantheon in this light stops being a relic. It becomes a mentor. Its fabric is a data set, a physical manuscript on durability we are only now learning to read. The research it inspires is a direct line, from the empirical genius of Hadrian's architects to the labs shaping our future resilience. This ancient temple is helping to write the next chapter of material science, proving that some forms of wisdom only grow more relevant with time. Raphael wanted to be buried there. He made that choice in 1520. He picked the Pantheon. That tells you something. It was a statement. The most famous artist of his time saw this ancient temple as the right place. He tied his name to it. That act, it lifted the building again. It helped change it from a Roman ruin into something else. A symbol for human creation. That's an example of a survival pillar. The Pantheon's place in our minds, its cultural weight. Artists have kept coming back to it. In paintings, it's often there in the background. This stable, ordered thing in a busy city. Canaletto painted its scale. Panini, he made it the center of his imaginary scenes. These weren't just pictures, they were a way of keeping it alive. They spread its image all over Europe. People who'd never see it in person knew what it looked like. It became an icon in the imagination, long before tourists, then literature. The diaries from the Grand Tour full of wonder, or its quiet role in modern books. It's like a character, a reference point for history, a way to feel time. When a writer needs something permanent, something beautiful that lasts longer than empires, they turn to the Pantheon. That repetition, it stitches the building into our stories. Now film does it. So many movies use the front columns to say Rome instantly. But the better ones use the inside. That light from the hole in the ceiling, the huge space. It creates a feeling, serious and full of awe. It's where scenes about history or belief or big questions happen. Every time it's on screen, for millions of people, its importance gets a little stronger. This constant presence in art, it builds a kind of shield. The Pantheon isn't just a building in Rome anymore. It's a monument to people, to all of us. Its value is global. That status creates protection. When something is seen as everyone's heritage, keeping it safe is a worldwide concern. Money comes from international groups. From donors who think they're saving a piece of human history. The best restorers in the world want to work on it. This cultural need works with the physical needs. The concrete fixes its own small cracks. The global community fixes the big threats. A crack in the wall isn't just an Italian issue. It's a World Heritage problem. That two-layer defense is deep. The building's own intelligence gave it 2,000 years. The world's admiration gives it the next years. That shared investment makes a community. Everyone, from the scientist on site to the visitor with a souvenir, becomes part of its life. It's a cycle. Its fame means it gets studied and seen. That attention pays for its upkeep and study, which teaches us more, which makes us care more. The Pantheon lives on not even though we look at it, but because we look. It showed us how to keep stone alive. And we learned how to keep it alive. The next guardians of the Pantheon could be silent and digital. A network of sensors, thinner than a hair, woven right into the old fabric. Fiber optic threads along the mortar lines feeling for strain. Tiny devices embedded watching the humidity, the temperature, the minute vibrations from the city itself. It becomes a living nervous system for the building, a constant stream of data, showing how the dome breathes with the seasons, how it settles after a heavy rain, how it responds to crowds. This isn't science fiction, it's the imminent future. Drones with thermal cameras mapping the dome's exterior, looking for temperature differences you can't see, finding signs of stress long before a crack appears. An artificial intelligence will analyze all that data. It will build models. It will simulate the dome's response to new threats, more intense heat, altered rainfall from climate change. The AI could answer questions we haven't even asked yet. What happens if the temperature range increases another 2 degrees in 50 years? What do more frequent downpours do to the drainage over a century? The models offer forecasts, so conservators can plan not as emergency repairs but as gentle preemptive care. This technology could guide restoration at a microscopic level. Three-dimensional printing might fabricate exact replicas of eroded pieces, a fragment of a cornice, a piece of a coffer's edge worn away by wind and pollution, reproduced in a compatible material, seamlessly integrated. to preserve the aesthetic and the original stone beneath. But the greatest challenge for future conservators won't be technical, it will be philosophical. How do you marry this high-tech toolkit with a deep respect for the original material, the ancient techniques? The guiding principle has to be minimal intervention. The goal isn't to freeze the Pantheon in a single moment, like a fossil in a case. That would deny its nature. The concrete is still curring, still reacting. The light still moves. The philosophy is stewardship, not control. It's about facilitating the building's dialogue with time, using technology not to stop the conversation but to understand it better, to ensure the dialogue continues for another 2,000 years. The tools will change, but the task remains to listen to the monument and to help it endure. All these pieces, the volcanic hills, the digital sensors, they're part of one story. The Pantheon's survival is a kind of historical alchemy. An improbable transformation. It took the dark ash from local volcanoes and transformed it, through fire and water, into a stone that heals itself. It took the empirical observations of generations, rules of thumb passed from master to apprentice, and transformed them into a geometry of perfect balance. It took the spiritual ambition to model the cosmos and transformed that into a physical form of breathtaking stability. And it took the simple, steady devotion of centuries, sweeping the floors, repairing the roof, praying under its light, and transformed that care into a continuous thread of preservation. These elements weren't separate ingredients added to a recipe. They were fused. In the intense fire of Roman ambition, they became an indivisible whole. The material couldn't have succeeded without the form. The form would have been meaningless without the cultural purpose. And that purpose would have been forgotten without the enduring physical vessel. This is the alchemy of permanence. A fusion so complete you can't point to one secret, one trick, one moment of luck. It's the system itself that endures. The building challenges our modern world where specialization creates silos. An architect designs the shape. An engineer calculates the loads. A contractor sources the materials. A client decides the budget. The layers are separate, negotiated, often in conflict. The Pantheon is the opposite. Here, the architect was likely the engineer, deeply familiar with the material's behavior from a lifetime of building baths and bridges. The client was the state, with the will and resources to demand the best. The spiritual meaning dictated the aesthetic, which dictated the structural logic. There was no division between beauty and strength, between symbol and substance. They were the same thing. This holistic unity is what whispers across 2,000 years. It asks a quiet, profound question. In our age of calculated efficiency and planned obsolescence, what are we building today that might carry a whisper of our own time to the distant future? What fusion of our values, our knowledge, and our materials could possibly speak so clearly, so compellingly, to a world we can't even imagine? The Pantheon offers no simple blueprint. It offers something better, a standard. A demonstration of what's possible when human creation aspires not just to function or to impress, but to become a permanent part of the conversation between earth and sky. That conversation with time, it's still going. And we're in it now. We've been through the layers of that story. The self-healing concrete from volcanic ash and slow chemistry. The Coffers and the Oculus, that geometry that turned weight into light. The big intelligent drum holding the dome's ambition and the stable ground that lets it settle in. There's the historical luck of its constant care and the cultural respect that became its armor. Each piece is a response, a Roman answer to an old question. How do you make something permanent? Their answer wasn't one secret. It was a whole symphony of solutions all playing together. The Pantheon's survival is a quiet argument. It says the height of innovation isn't always the technology. Sometimes it's depth of understanding. It's designing for endurance as the main goal. Building a dialogue with natural forces, not a declaration of dominance. This old structure challenges our modern speed, our disposable culture, our narrow idea of progress. It stands for holistic thinking, where material and form and purpose and legacy were all one thing from the start. So when you see that serene interior again, or the familiar columns of the portico, don't see a frozen artifact. See a living lesson. A reminder that the most advanced solutions for our future, sustainable materials, resilient design, long-term thinking, they might be waiting in the deep wisdom of the past. What enduring legacies are we building now?